looking specifically at functions written as sets, we would like to be able to look at a relation and determine if that relation is a function or not. Then I'd like you to be able to list the domain and the range. When I'm trying to determine if a relation is a function when it's written in set form, I'm looking at the domain values. Just like we said before in the definition of a function, every element in the domain has to correspond to only one element in the range. So the domain is the one we're concerned about that cannot be mapped to more than one range. Some teachers say here that the x's can't repeat. One way of thinking about it is if the domain are, let's say, guys, and the range, the y values, are the ladies, every x, every guy, can only be dating one y. On the other hand, the y's, the ladies can pretty much do whatever they want. It's the x values that need to be on their best behavior. The x ones can only be mapped to one y. So 10 is being mapped to 8, 6 is being mapped to 4, 2 is being mapped to 0, and -2 is being mapped to -4. Are any of these x values repeating or being mapped to two different y values? And no, it looks like all of these domain values are on their best behavior. So is this a function? Yeah, it is. My x's don't repeat to different y values. My domain is just the set of all first elements, or in this case the x elements. So I'm just going to list them 10, 6, 2, and -2. The order doesn't really matter here so much. The range would be 8, 4, 0, and -4. Let's look at relation K. I'm looking again at my domain. My x values can only be mapped to one y. My 3 is trying to date 4. My 3 is trying to date 5. Oh, wait a minute. That's not okay. Notice this 3 right here and this 3 right here are values in the domain that are trying to map to two different values in the range. One way of thinking about it is 3 trying to date 4 and 3 is trying to date 5, and that's a no-no. X's have to be on their best behavior. Another way of thinking about it is if you take your function machine, if this was to be a function and I plugged in 3 and I get out 4, then I would expect to get out 4 every single time. And the next day you plug in 3 and now you're getting not 4 but you're getting 5. You're like, hey, this machine is broken. In fact, it's not even a function at all. It's not a function machine because the function machine does not work. Now, just because it's not a function doesn't mean it doesn't have a domain. The domain is just the set of all first elements, or x's. 3, although I don't write it again. 8 and 1. My range is 4, 5, 9, and 0. On the last relation, I want to know if this relation is a function. I'm looking again at the x elements, and if any of these are repeating, then I need to take a closer look. 4 is being mapped to 5, 6 is being mapped to 8, 8 is being mapped to 8. Now that's okay, because the range can do whatever it wants. We are only really caring about the domain, the x values. So it's okay that the 8 appears twice. What's a little concerning is that we have 2 6's. Now let's take a look at those 2 6's a little bit closer. This 6 is being mapped to 8. This 6 is being mapped to 8. Is that okay? Yeah, that's exactly okay, and the reason is because the domain 6 is being mapped to the same range. This 6 is trying to date 8. This 6 is trying to date 8. Is that okay? Absolutely, that's just a second date, okay? That you're allowed to have a domain mapping to the range twice, as long as it is the same value. So is this a function? Yes, it is. Just because the x's repeat does not make it not a function, because they map to the same range value. That does make it a function. My domain here is the set of all x values, 4, 6, 8, and 6, although I don't have to write 6 again. My range would be the set of all y values, 5, 8, 8, and 8, which I don't write over again. And that completes our study on functions as sets. The next thing we're going to look at is functions as equations. The first thing we need to learn when we're talking about functions as equations is a new notation called function notation. And it's another way of writing an equation, which happens to be a function. Not all equations are functions, So function notation is only used for equations which happen to be functions. Function notation defines the range, or output, or sometimes we call that the value of the function, by using any value in the domain, which we usually call that x. If an equation is a function, then we substitute y with f of x, and we pronounce that f of x. So given the equation y equals 3x plus 1, I can rewrite that in function notation as f of x is equal to 3x plus 1. The f of x is giving me the output, or the range, in terms of x, which is part of the domain. So to find a value of the function at a given number, or at a given variable, or even at a given expression, we substitute the given number, variable, or expression into the equation and evaluate, that is if it's a number, or simplify if it's a variable or expression. Let's look at our first function, f of x equals 2x minus 3. I would like to find f of 5. Notice that in my function is defined in terms of x, but I'm taking x out and I'm replacing x with 5. So in my function f of x is equal to 2x minus 3, I would like to erase the x and replace all x's with 5. Because 5 is a number I can evaluate, 2 times 5 is 10, minus 3 is 7. So f of 5 is equal to 7. Because 5 and 7 are both values, f of 5 equals 7 gives me an ordered pair, a corresponding ordered pair, where x is 5, which is the input, and the output is 7, or part of my range. So f of 5 equals 7 gives me the point 5, 7. Next, I'm going to find f of negative x. In this case, I don't have a value here. I have a variable or an expression. But I'm going to do the same thing. F of x is equal to 2x minus 3. But I'm going to come in and erase my x's and replace all of my x's with negative x. When I simplify, I get negative 2x minus 3. So f of negative x is equal to negative 2x minus 3. Next, we're looking for f of x plus 1. Again, I write my equation f of x equals 2x minus 3. I'm going to come in and erase all of my x's so that I can replace my x's with x plus 1. Next, I am going to evaluate by distributing the 2 to get 2x plus 2 minus 3, and f of x plus 1 equals 2x minus 1. We'll try a few more examples. This next one, g of x equals x squared plus 3x plus 5, is a quadratic example, but I'm going to be doing the same thing. Even though there's more than one x involved, every time I see an x, I'm going to replace it with whatever the value or expression that's inside the parentheses. So if I'm trying to find g of negative 2, I still start off with the function x squared plus 3x plus 5. Then I come and take my eraser, and if I'm going to replace x with negative 2, I have to do it on all locations where x appears. So g of negative 2 is equal to negative 2 squared plus 3 times negative 2 plus 5. So I can evaluate and get a value of the function at x equals negative 2. Negative 2 squared is 4 plus 3 times negative 2 is negative 6 plus 5. Getting negative 2 plus 5, or 3. Therefore, g of negative 2 is equal to 3. Next, I'd like to find g of negative x. Negative x is an expression, but I'm going to do the same thing. G of x is equal to x squared plus 3x plus 5. Every place that I see an x, I'd like to come in and erase and replace the x with the expression that's inside the parentheses. This time I'm replacing with negative x. When I simplify this expression, negative x squared means negative x times itself negative x, or positive x squared. Oops, I forgot one. 3 times negative x is negative 3x plus 5. So therefore, g of negative x equals x squared minus 3x plus 5. Lastly, we have g of x plus 3. I'm going to come into my function and erase all x's so that I can replace all of my x's with x plus 3. Now I can simplify. When you square a binomial, don't forget that you have to either know your perfect square trinomial formula in your head, or you should write it twice and distribute. Because x plus 3 squared means x plus 3 times itself x plus 3. You can find those last like terms there. Finishing this problem up, I'm getting x squared plus 9x, and 9 and 14 make 23. Therefore, g of x plus 3 is equal to x squared plus 9x plus 23. Our last function, h of x, is equal to x squared over x minus 1. I'm first asked to find h of negative 1, so I use my original function, h of x, and then I come in and erase all the places where x is located, and I'd like to replace x with negative 1. Because I have a value here, I can evaluate and get negative 1 squared is 1. Negative 1 minus 1 is negative 2. Therefore, h of negative 1 is equal to negative 1/2. The corresponding ordered pair would be negative 1 comma negative 1/2, where negative 1 is the input and negative 1/2 is the output. Next, we're looking for h of 4. This time I'm not going to erase, I'm just see if we can go straight for it. H of 4. So I'm replacing x in my original function with 4. And then because 4 is a value, I can evaluate. 4 squared is 16. 4 minus 1 is 3. So h of 4 is equal to 16/3, and the corresponding ordered pair is 4 comma 16/3. Lastly, I'd like to find h of negative x. Again, every time I see an x in my function, h, I'm going to plug in a negative x. And now I have to simplify. Negative x squared is negative x times negative x, which happens to be positive x. Negative x minus 1 cannot be simplified, it's just negative x minus 1. Therefore, h of negative x is equal to x squared over negative x minus 1. That one doesn't have a corresponding ordered pair because we have an expression as our input.